Hello everyone, I'm Charles Carrier. I'm research fellow at the Bristol Composite Institute, and today I'm going to present a study that we've conducted with Fabrizio Scarpa from the same department and James Armstrong from the medical school of the same university, called Flax fibre-reinforced alginate-poloxamer hydrogel, assessment of mechanical and 4D printing potential. This study has been sponsored by the European Research Council and EPSRC, and part of the equipment has been funded by DSTR. So we thank all of them for their support. So what is 4D printing? 4D printing is a technique that is inspired by, among other things, pine cone. So pine cone, if you don't know, open and close by its change in their environment. And this has been optimized by nature in order to be able, for the pine cone to be able to release their seed at the most appropriate moment so that they could reproduce and spread further, basically. The way they do this is that in the pine cone scale, there is bilayer structures in which you have different holes in the different scales, in different layers, sorry. And these different holes create different properties of the material which interact differently with the environment, basically. And if when the one layer wants to expand, the other one doesn't want, it creates stresses at the interface of the two layers, and therefore bending of the pine cone scales. And we want to use the same principle of engineering, and we have in the past. We created a literature review published in Advanced Functional Materials, which discusses most of the things you need to know about 4D printing hygromorphs, so related to actuations. And you can find 40 pages of a lot of study that has been published in this field, if you're interested. We created our own actuators, 4D printing actuators, out of continuous flax fiber reinforced polylactic acid, which, as you can see, has a three-layer structure, so it's very similar to the pine cone scale. These three different layers interact differently with the environment. So when you change the humidity, it tends to some want to expand, others don't want, and therefore you have stresses at the interface of this layer, and therefore bending of the structures. So in this study, published in Material and Design, we look at the design space, so how the printing pattern influences the result the actuation that we get at the end. And so if you're interested in 4D printing, you can have a look at the structures that we've created. So how did we end up working with hydrogels? It's basically my favorite researcher, Maria Skłodowska-Curie. One day I was waking up in the middle of the night in front of a big poster that I've got in my room of her. And I say, I know what I need to do now. I need to use the same technique that I know and put it in medical application. And the reason why she inspired me is because during the First World War, a lab was closed. And she used her knowledge on X-ray and radiation in order to create little portable radiographic inspection device, drove them to the front line and help doctors saving British and French lives on the front line. I'm not comparing myself in any shape or form to her, but I wanted to do the same thing, basically, use my knowledge and go to medical application. And that's what I did. I went to James Armstrong, and we created, who works in the medical school, and we created this material out of flax fiber reinforced with alginate-poloxamer hydrogel. The proportion of material in this hydrogel are found in this table. It's mostly water, sodium alginate-poloxamer, flax fiber, and it's cross-linked with calcium chloride. And the reason why it could be used in biomedical application and medical application is, for instance, this little structure on the right is cylinder, which is the exact dimension of certain aorta in human and animals' body. And so that's kind of the structure that we wanted to create in this study. In order to do this, we went to France, asked Ecotechnina to provide us with some fiber, and they very kindly accepted, and we thank them again for this. We put this continuous flax fiber, crush them into a planetary ball mill, and obtain a little paste out of it. And we put this paste into poloxamer and alginate and created an hydrogel out of it that we mix in a speed mixer DAC and then 3D print it before cross-linking after printing. Then we 3D printed three different types of specimen, printability, mechanical test specimen, and 4D printing specimen. And that's what I'm going to talk about today. First test I'm going to talk about is fusion filament test, which is a test in which you 3D print your filament next to each other with increasing distance. And you look at the distance at which your filaments stop fusing with each other. And so the slightly yellowish specimen are with flax fiber, while the white one are without flax fiber. We are able to see that with the addition of flax fiber, our material is able to keep itself a bit more together, and you can print with greater resolution, basically. And so our addition of flax fiber enables more precision into the printing. Another aspect is the annulus scaffold, so it's the images I've shown before. Without flax fiber, we cannot print that kind of cylinder because it collapses on itself. It's not able to withstand its own weight, basically. With the addition of flax fiber, we were able to obtain a cylinder up to 6.5 millimeters and with fairly good repeatability, basically. So it increases the design space again for the type of material, and therefore addition of flax fiber is important, very interesting for printability purposes. The last printability test that we conducted is collapse test. It's a test in which you 3D print your material on top of pillars, which have different distances between them, increasing. And for us, it was between 4 and 10 millimeters. And then you look at if your material is able to withstand this self-weighting between different pillars, and the shape that you obtain as well in order to obtain mechanical properties out of it. So you have a camera that look on the side, and then we are able to measure the failure rate for the different materials. So without flax fiber, there is no failure between 4, 5, and 6 millimeter gap, but at 8 there is 30% failure rate, and at 10 there is 70% failure rate. With flax fiber, there is no failure rate for any gap whatsoever. And therefore, the flax fiber enables us to print more different structures, basically, with this as well, which is very beneficial. So this specific collapse test was not standardized for our specific type of materials, and we needed to go deeper into the standardization of this test for our materials. And we published a paper specifically of standardizing this this test, and adapting it to very soft material. We also used this technique in order to measure the properties that we could not measure with a normal tensile test. In the tensile test, the tensile properties of the material before cross-linking. Before cross-linking, the material is very soft and cannot hold into the grip. And so we use the collapse test in order to make these measurements. And the way to conduct this test is available in this paper if you're interested. Then we conducted our tensile test. So tensile test, we wanted to look at the influence of the amount of flax fiber onto the properties of the tensile test. And so we produced little dog bones, we loaded them into tension and obtained the stress strain curve in here, measured E1, E2, the strength and the strain at fracture, which are displayed on the right side of the screen. You can see that generally if you increase the amount of fiber, you increase the stiffness E1 and E2 that you obtain. However, after 1%, it doesn't increase a lot anymore. And for most of them, it's statistically equivalent. In terms of strength, the 1% fiber weight fraction is the best. And in terms of strain at failure, it's between 0.5 and 1, which are statistically equivalent. But overall, the best parameter that we can find is 1% fiber weight fraction, especially because you have more defect if you add more fiber. As you can see, the standard deviation for the 3.5 properties of fiber weight fraction properties are massive compared to the other one. And therefore, we consider for the rest of the study 1% fiber weight fraction. We also provide a small database of alginate-based hydrogel, which conducted exactly the same test, showing that our material is approximately average compared to the rest of the test. But if you need to have information about the different material you could use to obtain a good stiffness of alginate-based hydrogel, and cross-linking techniques or additives, you can have a look in this small database available in the paper. Another aspect that we considered is, so tensile test is good, but when I was running, I was wondering if we want to use this material inside a human body, it's going to have a lot of cyclic loading. Basically, for instance, when you run, you have cracks that could propagate slowly and slowly. You don't want a brutal failure, basically, otherwise the material is going to just break and get destroyed quickly. So you need to dissipate energy when it is impacted again and again, for instance, during a run. One way of doing this is measuring the area under the curve during the tensile test, which represents this amount of energy dissipated. And we're able to see that the fiber weight fraction is again 1% ideal to obtain as much energy dissipation as possible. In order to understand how this energy is dissipated, we conducted a small factographic inspection in which we looked at different failure patterns, such as crack branching or crack deviation, that were observed and are influenced by the flax fiber in order to dissipate as much energy as possible. If you're interested by the fractography of that kind of materials, you can find some information in here. One of the key aspects we wanted to conduct is a comparison between our material and literature. And we don't just want to compare the materials, we wanted to compare the stiffening ability of our additive flax fiber. So we look in the literature. The test that is most widely conducted is rheology. So we went to our remitter, printed some circular disc, and then shear our specimen. We shear our specimen with flax fiber and without flax fiber, and we're able to see that the addition of flax fiber stiffens the material. It makes it more viscous. But you still have this decrease on the right side of the curve at high strain rate, which is important in order to be able to lower the viscosity during printing. Then we wanted to compare that data to the literature, and so we looked at the range of tests that has been the most widely available in literature, and the most common one is between 1 and 5 second minus 1. We consider these 2 points. We consider what we invented a new coefficient called the stiffening coefficient, which represents the difference, the relative difference in viscosity between the reinforced and the non-reinforced material, in our case reinforced with flax fiber. And we compared the value obtained for our material to the one available in literature, for instance, cellulose nanofiber, algae, or nanoclay. And we created again a small database. If you want to stiffen an hydrogel, you can go to this database and find the adequate stiffening material for yourself, for your applications, basically. Then the 4D printing part. So if you want to use 4D printing material and hydrogel inside the human body, most likely they're not going to be 3D printed inside the human body. So the conditions of 3D printing are going to be different than the conditions of use inside the human body. And we need to predict how it's going to deform the material inside the body. And that's why 4D printing comes handy. We printed some specimen, what we called in composite science 090 stacking sequence, meaning we're 3D printing in one direction, and the second layer was 3D printing in transverse direction at 90 degrees. For the two, 1% and 0% fiber weight fraction. Then we dry them and look at the actuation. We obtain the same kind of actuation, a curved specimen. We're able to see on the graph on the right that the curvature decreases with the addition of flax fiber. So the addition of flax fiber allows to control the actuation obtained. We are also able to understand that the addition of flax fiber allows to maintain a shape closer to the initial one, basically. And this is due to the fact that the flax fiber are printing aligned in the direction of printing, and in their length direction, they are difficult it's difficult for the material to control it on itself because it is all held by the flax fiber. And this we relate to a specific concept that we developed in the literature review we created at the beginning. I talked about at the beginning. It's the difference between fiber and matrix-dominated actuation. In the continuous flax fiber PLA that we've showed at the beginning, we have fiber-dominated actuation, meaning that it's the fiber that expands and contracts, and therefore pushes and pulls the matrix, creating the overall deformation of the structures. For the matrix-dominated actuation, it's the matrix that expands and contracts, and then the fibers' role is to prevent the deformation in their length direction. Preventing the deformation in specific direction will allow the material to create some stresses at the interface if the fibers are not aligned the same between the different layers, and therefore create the bending. And that's exactly what we have in our specific material. If you're interested by that kind of concept, please have a look to our literature review. In our soft matter study, we looked at the influence, the orientation of the fiber. So we use a tensile test specimen, cut it, and look at the orientation of the fiber, and we're able to see that the fiber are orientated toward the printing direction, confirming this hypothesis of matrix-dominated actuation triggered by the flax fiber orientation. Finally, we looked at more complex structures. So this is a flower actuators, which is inspired by a flower, basically, and the first layer are concentric circles, second layer are inspired by a flower patterns. And therefore, you have to imagine that there is, at each contact point between the first and the second layer, there is an actuator, a small actuator, basically, a discrete actuator. And therefore, depending on the orientation between the first and the second layer at each individual contact point, and the position of each individual contact points, you can create some complex actuation. And that's what we wanted to illustrate with this one. There is potential for creating complex actuation out of this material. So I will say thank you very much for listening to this presentation until the end. Again, thank all the sponsors and all the people who worked with me, and I wish you to see you in other presentation on the channel. Thank you very much.